Okay, perfect. So thank you, everyone who is participating today. We will speak about a real-life application of our radio module, the MAMWLE. Today we will have some guests. I will be presenting them later. So I'm really happy of this webinar because we will see something that is solid. It's the first time that we do something like that. We have already spoken about a use case. It was a practical one, but not a real life. So hope it will be interesting also for you. For me, it's an honor to present it. So let's go on. In particular, we will be speaking of an IoT landslide early warning system. Our guest will be later speaking more in depth of what is the use case in particular. I will start speaking about my company. The name of my company is Movax. We design embedded system. So we are in the embedded system industry. So we are now having two main products. The first one is the MAMWLE. I will go in deep later in the product. The second one is the Cicerone board. It's a LoRa one plus GNSS product. Yeah, the company designed mainly these two products. We have I don't know why it's not proceeding. Okay. Yeah. So we have the mission of doing the world smarter in the IoT industry. And also we have the aim to leverage the potential of new technology and to bring a positive change into the world. And that's how we picked our guest today, because we think that we are sharing the same mission. So we will be speaking Giuseppe Reale from the HDM Group, HDM. maybe you already know them like HDM in Italian. He's an hardware and firmware engineering, and he will be speaking about their product. Their product is a DVK, LoRaWAN DVK based on our MAMWLE. It's a really good product if you want to test our radio module. So I will suggest to reach out to them to get your hands on the board and to start playing with the module. Also, I have to say that the board is on discount in the end of the webinar. I will be saying how you can get the discount on the board, and it's a good opportunity to start developing with our LoRaWAN module. So let's say that this board is the first part of this IoT Landslide product that has been developed by Emanuele Tavelli and Francesco Antolini of Winet and Geosolving. It's really a brilliant application, and we are happy that our radio module has been part of a brilliant application like that. So they will be speaking in deep on about what they have installed, and you will be. I hope you will find them interesting. So I would like to go in deep on our product. It's a LoRaWAN module. It's a special one because we have a really power core, is the STM32 with a Cortex M4. You can find 4 different versions of our module. That depends on the antenna plug, that could be UFL or PAD antenna, and on the flash RAM capability. So it could be two different versions, a bigger and a smaller one. That's the core of our webinar, and it's already part of a lot of brilliant application where we are really proud of the product. I will say that it's the star of our company. The special thing about the module is that you can use it and easily program it for different band. So you can tune them to be used in all the band that goes from 868 to 915 megahertz. So everything that goes in Europe, US, Australia, and so on. And we have certified them to be used in Europe and USA without problems. So another special things is that we are using, we included a lot of GPIO. We have a number of GPIO, that means a bigger versatility in confront with the other module on the market. Because we take the STM32 and we try to bring all the different features outside. So that's good, because you don't have to do like a puzzle in your PCB to access to all the features that you may need. Here you can find a schematical of how we designed it. We have the STM32, we have the TCXO included, and also the RF design is already on top. Like I was saying, we have 2 types, the PAD and the UFL. And it's really tuned to be power efficiency. So we have a smaller consumption in confront with the other competitors. So that's a bit something about our radio module. And I will, with that, leave the word to Giuseppe Reale, that will speaking about the board that they have been developing. So Giuseppe, if you want to, hello.
Hello, hi everyone.
Hello.
Thank you, Ilenia.
So thank you for joining. I will leave you the word so you can speak about the board that HDM development.
Okay, so, thank you, Ilenia. Share my screen. So, hi everyone. I am Giuseppe Reale, hardware and firmware engineer at HDM Group. HDM was born as a system integrator by merging creation with data management. But we are more than that, because we make innovative hardware and software technology tools to meet the customer requirements, starting from the design and the development of sensors that generate data, up to the development of algorithm for artificial intelligence, monitoring and forecasting, real-time analysis, and much more. Our team is able to support the customer at all stages of the project, starting from the feasibility study and the scouting phase, continuing with the custom development of hardware and software, up to the production, setup, and after-sales support. Our approach is to support the customer in a collaborative way, giving our competencies also for consulting and management. For one of our internal IoT project, we had the idea of developing this LoRa prototyping board using the MAMWLE module. So we proposed the idea to Movax, who accepted it, and from there started a nice partnership between HDM and Move-X. The MAMWLE DVK CB01 is a complete development kit consisting of a carrier board mounting an LoRa node, which integrates the MAMWLE module. The LoRa node is a compact and versatile radio board, which is compatible with different types of antenna and which can be interfaced to different types of sensor and actuators with analog or digital input-output. The carrier board is used to easily interface the LoRa node to different types of sensor and actuators thanks to the Arduino Uno R3 standard connectors. And also the carrier board can be powered via a standard USB Type-C connector and can be fixed with screws thanks to the 4 M3 holes placed at the corners of the board. So the carrier board with the LoRa node constitutes the development kit useful for evaluating the functionality of the MAMWLE module and to develop application based on it. Going into more details, the LoRa node consists of a PCB whose core is the LoRa node MAMWLE11, manufactured by Movax. It also includes a PCB antenna and the provision for mounting a connector SMA or UFL for any external antenna. In addition, the board is equipped with a rest button and the provision for mounting a mini programming debugging connector. Side pads are also provided for surface mounting of the node on the carrier board, which are connected to all the pins of the LoRa module and therefore act as input for the power and input outputs for analog and digital signals. If not needed, the PCB antenna can be easily removed by cutting the 3 points where it is connected to the rest of the board. Furthermore, on the bottom layer of the board, there is the provision for mounting 2 board-to-board connectors, which act as input for the power supply and input outputs for the analog and digital signals. They are very useful if the node must be mounted on a motherboard with a compatible connector. The LoRa node is very compact with a dimension of only 45 by 57 millimeters with PCB antenna and 45 by 36 without. The supply voltage can be from 1.8 to 3.6 DC voltage, while the standby current is 1 microampere and the peak current is 120 milliamperes. The PCB antenna is designed for LoRaWAN protocol at 868 MHz, and the range of transmission is about 1.3 kilometers. Furthermore, the node has different kinds of communication interfaces for embedded systems, such as I2C, SPI, USART, ADC, and GPIO. While the carrier board is a PCB with a power supply section, USB Type-C connector for 5-volt power supply, Arduino Uno R3 connectors for interfacing with external sensor, a programming connector, a user button, and a LED. While the intelligence is represented by the LoRa node, which is mounted on the carrier board via pads for surface mounting. The dimension of the carrier board are 70 by 116 millimeters with PCB antenna and 70 by 95 without. The supply voltage is 5 volts from USB, but the carrier board has an internal 3.3 volts regulator able to deliver more than 2 amperes. While the communication interfaces available on the Arduino Uno S3 connectors are the same of the LoRa node. There are many fields of application of our LoRa node. For example, we have already integrated it in a project in the field of waste management to interconnect a smart bin lock. Furthermore, the LoRa node is used by Geosolving and Winet in a landslide monitoring system. So I hope I've given you a clear overview of our development kit, but if you want to know more, you can contact us by phone or email. I also invite you to visit our website, hdmgroup.it, where you can consult our catalog and explore all the other solutions we offer for the IoT and beyond. So thanks for your attention, and I now leave the floor to Emanuele, who will explain a use case of our DVK. Thank you.
Okay. Hi everyone. I'm Emanuele Tavelli from Winet, and there is also Francesco Antolini from Geosolving. And in this presentation, we will explain all the details about the geoAndes early warning system. Okay, let's go. Winet is a young company born in 2011 that deals with the design and implementation of wireless sensor network, or in modern terms, IoT devices. Especially, we work in precision farming and landslide monitoring. In these two pictures, you can see a typical installation of this kind of system. In the left one, you can see a VSN node, in this case, a coordinator node with a GPRS connection, connected to a crack meter and a tilt meter sensor. In the image on the right, you can see a typical weather station. So we have air and humidity temperature. We can have a rain collector and an anemometer. Winet is a young company and is a tech integrator. So usually the network is made up of a series of nodes equipped with one or more sensors, and all the nodes acquire and send data. In this example, you can see a mesh network that acquire and send the node to the cloud with a coordinator node. In this case, we have a GPRS connection and the data is sent to the cloud. Okay, but as I wrote, we choose the best technology to satisfy the customer needs. So in this case, we have a VSN, but we can have a LoRa, we can have a narrowband IoT. So we choose the best technology. For example, in this slide, you can see an overview of the geoAndes systems. And as you can see, we have a lot of technology. This system is composed by different parts. We have a webcam with the 4G LTE transmission. We have a weather station and a wireless node with the 2.4 gigahertz transmission to a coordinator node. And the coordinator node is the brain of the system. So in this case, our coordinator node is composed by 3 technologies. We have a VSN 2.4 gigahertz antenna, we have LoRa antenna, and then we have a GPRS connection to the cloud. we use the development kit of the Move-X HDM in the coordinator node and in the LoRa receivers. The LoRa receivers are connected to the traffic lights, and in this case, there is a warning. With the LoRa connection, we can turn on the red or the yellow light on the street. As you can see, we have a geoAndes web app, and from this web app, we can manage all the system. We can, for example, change the acquiring time, change the transmitting time, or turn on the red light. We can do all from the web app. Okay, I give floor to Francesco Antolini that will explain in details why we can we develop this type of system and which are the problems we would try to solve.
Okay, so thank you very much, Emanuele, and good afternoon to everyone. I would start giving you a very brief presentation of the Geosolving company. I am a geological engineer, and Geosolving is an engineering company based in Torino that mainly provides services and solutions in the geoengineering field. We are, as I said, civil engineers and geologists, and the company was born in 2013 with the name of Resolving, as you can see here, and we are a former spin-off company of the Politecnico di Torino. We are specialized in advanced numerical modeling to solve geological and geotechnical issues, energy geostructure design, and monitoring and the early warning system. Among them, here you can see the geoAndes system, that is the main topic of this on this webinar, and which I'm going to show you in the next slide, as well as other projects which we are already developed, such the EVUSAR system, that is for automatic processing of displacement and velocity maps obtained from ground-based interferometric synthetic actuator, and the OptiAlp system, which we are currently testing and developing. I think this project is quite interesting and promising, since for OptiAlp we are using distributed optical fibers for the early detection of the occurrence and avalanche and debris flow. But this is another story. So let's start with the description of the of what we are looking at. So with the geoAndes system. So I'm a geologist, so I'm probably much more familiar with this kind of natural dangerous phenomena. But for clarity, I think that two very short definitions are now required. Debris flow, so debris flow are a particular type of landslide. There are fast-moving landslides made up of a mixture of water, rocks, and debris that are particularly dangerous to life and property because they move quickly, destroy objects in their paths, and often strike without warning. Similar to debris flow, we are dealing with avalanches that are rapid flow snow that is occurring down a slope such as a hill or a mountain, and they are primarily composed of flowing snow and air, but also there they are capable to move, have the capability to capture and move ice, rocks, soils, and trees. So the common feature of both these two mass-moving phenomena is the capability, as I said, to move quickly up to 100 kilometers per hour and more, and travel for long distances. So from the point from the point where they originated, which corresponds to the upper portion, as you can see in these pictures, in the upper portion of the mountains, and they move to the bottom of a valley typically. This characteristic, of course, made these debris flows and avalanches very dangerous for all the elements exposed to the risk. That means people, houses, villages, linear infrastructure, and so on. So they particularly, for instance, debris flow occur as a result of very intense rainfall, which are, as you can probably able to say here, that are more and more frequent in the Alpine. So now, after this brief introduction, let's see the specific site where the geoAndes system has been applied. So back in 2017, to make this story short, the autonomous region of Valle d'Aosta at first, and then the Cogne municipality asked us to design and for the design and the development of a monitoring and early warning services to mitigate the risk of debris flow and avalanches that are occurring along this access road to the Valmonte villages. This road is located at an elevation between 1,000 feet and 500 meters above the sea level, as you can see there, and is crossed by two gullies that are called Buvat Gully and Pontef Gullies, that are very deep and steep current in incision that represent the main output of two sub-basins, as you can see there, that are located on the left flank of the Dora di Valmonte Valley. So to extremely simplify, this means that there's no avalanches or the debris flows could travel along these incisions and travel and reach the bottom of the valley and cross the road in here. You can see in the yellow circles, interrupting at the same time the access to road to Valmonte. Obviously, as you can imagine, this is extremely dangerous for vehicles and people traveling along the road. Please note that this is the only access to the Valmonte villages, and these villages, even though is very small, some people live there all over the years, and in winter and summer is a very touristic place because it is one of the main access to the Gran Paradiso National Park. This means that that a very high risk along the road is present, and so someone needs to do something. So we have developed and installed the geoAndes system. So at first, here you can see an overview of the system. We were asked to deploy a system for one of the two gullies that is called the Buva Gully. Therefore, after few site inspection, a lot of brainstorming with all our colleagues in 2017, we have designed a specific early warning system based on a single trigger line, as you can see there, two traffic lights placed along the road, two cameras, and one weather station. Each element is equipped with a specific radio nodes in the framework of the creation of a wireless sensor network, and this is provided by Winet, as Emanuele said. At the beginning, the main issue we need to face is the correct positioning of each element of the network, since we had a lot of constraints. Overall, one of the main constraints that we need to face is the accessibility of the place to install the trigger line along the gully. And this is very challenging because the places are difficult to reach, and this was overcome by defining a correct distance between this position, this trigger line, and the traffic lights. The invasion areas are another very challenging requirements, because the traffic lights need to position it outside the invasion area, because all the vehicles that stop along the road needs to occupy a safe, obviously a very safe place. Then to overcome this, to overcome the distances and the problem of communication between the different radio nodes, we use the LoRa kit, and this was with this we were able to overcome these problems, and so we were able to deploy and install the early warning system as shown here. Here is it. I'm showing you particular or a detail of the trigger line. This is formed by tilt sensors. These tilt sensors were suspended on ropes, on wire ropes, and there were two cables, one structural cable, one positioning cable, and each of these tilt sensor is linked to a counterweight that is directly suspended above the channel where the snow or the debris occur, and when this is hit by the mass, this plate rotates, and so the tilt sensor is able to measure the differences between the vertical position and the effective last position, and by using a specific threshold, it is possible to generate an alarm signal. So this is a detail of the WSN, the wireless sensor network gateway that is the coordinator node that performs the continuous interrogation of the tiltmeters, generates, as I said before, the alarm package for turning on the traffic lights if the alarm threshold is exceeded, and collect and sends all the data to NFTP through a 4G connection. So these are some images, some picture which show the detail of the installation of the WSN coordinator node. These are pictures of the traffic lights which were installed along the road, and this is I want to stress that each traffic light is equipped with two lamps, one red light to indicate the road closure, another yellow light that is flashing to indicate possible danger, and then a further camera has been installed to monitor the road. This picture is a detail of the installation of the electronic boards that are assembled inside the cabinet that you are able to see here. And this is the weather station that is equipped with a pluviometer, a thermometer sensors, and an anemometer. And this is completely powered by batteries and photovoltaic modules. So it's completely standalone from all the other elements of the wireless sensor. So after a few years that we were installed the early warning systems on the Buva Galli, we were asked also to install another system along another galley that is, as I showed you before, is located very close to the first one. So we were asked by the Cogni municipality to develop this early warning system, and this task was a bit more challenging than the previous, since this galley is characterized on average by an higher frequencies of occurrence, both of avalanches and debris flow, and by the fact that the potential invasion areas along what we called the alluvial fan, our geologists would call alluvial fan, this area here is much more larger than the one that is present on the Buva Galli. So therefore we were forced to install two different trigger lines that we call number one and number two, trigger line number two. to have sufficient time to detect the passage of the mass on the trigger line and stop the traffic before the mass will reach, obviously, the road. In this case, from the beginning, we already used the LoRa tracer receivers to do this job, because also in this case the distances between among the different nodes are quite larger. So we have to overcome this problem of communication between all the different radio nodes. So in this case, for the trigger line, we used wire sensors. Then I will show you a detail in the next slide. Here you can see the trigger line number 1. We installed 2 different wire sensors across across the channel, and this is a picture of the camera and the control node. So we have obviously a control node and a camera that is able to take pictures every 1 hour or 2 hours. What is the situation along this channel. So this is a detail of the wire sensor that is formed by 2 switches on-off switches. So the switches they're closed when the wire is tensioning. This is the case of the switch number 1, or when the wire is breaking, and this is the switch number 2. So when this happens, a specific signal is generated, and so the traffic lights are turned on. So now in the next slide, I will show briefly how does the functioning of the system. So when there is no alarm, the system is collecting data. So as I said before, the coordinator node is able to interrogating for instance, here you can see the Buva, the situation and the scheme of the Buva Galli. So is interrogating the tiltmeters and all the node, and is able to collect and send data in over internet. And so every maybe 20 or 15 or 20 minutes, the user can see if everything is okay, and obviously the road is open to traffic and no alarm is triggered. Another possibility is to turn on the yellow light flashing. This function is to be used mainly in unclear situation, for instance, during heavy rainfall, snowfalls, and whenever the system does not work properly, so as not to exclude human control. And this means for the vehicles that travel along the road that the road is open, but possible danger is present along the road. So particular caution is required, and a speed limit is envisaged along the road. The last option is during the functioning is when there is the occurrence of the avalanche or the debris flow along the channel. Then in this case the tiltmeters overcoming the threshold. So this is in real time sent by to the collector, to the coordinator node. So the coordinator node generates the alarm. They turn on the traffic lights to turn on the red light, so the traffic is blocked along the road. And then an SMS and email are generated and sent to specific recipient of personnel, which is in charge of the management of the security along the road. For instance, in this case, the technical people of the municipality. So this is as Emanuele said before, is completely, the system is completely manageable through the geoAndes app that allows to easily check the monitoring network status, sensor cameras, traffic lights, as well as we can query the graphs showing the measured data. So you can manage all the system through this app. Now, to conclude, I will show you some of the some events that we were able to see, to capture in these along these two galleys. The first one is an avalanche occurrence in 2018. So after maybe 3 or 4 months after the first installation of the BUVA early warning system. So you can see the trigger line before the avalanche occurrence, and this is after the avalanche occurrence. So you can see a huge amount of very wet snow that is propagating along the channel. As you can see here, we have all the counterweights that are linked to the tiltmeters. So this is the mass has hit the counterweight, and the specific thresholds on the tiltmeters were exceeded. So the alarm was sent to the traffic lights. We were lucky because in this case the avalanche, as you can see here, stopped about 30 meters above the road. Here you can see after the generation of the alarm, the personnel of the municipality was promptly informed, and here you can see a vehicle that is going through the road, and someone has arrived to check the situation. The road now is closed, but this is a vehicle of the municipality of Cogni, has checked that the mass has stopped about 30 meters uphill. And this is we were particularly unlucky that year, because after 3 months another great avalanche occurred in April, in the 14th of April, and here you can see in this case a huge amount of snow is coming down and has reached and interrupt completely the road. As you can see in the red circle, you are able to see the position of the traffic lights. And in this case, I want to stress that the position of these two traffic lights was obviously designed in order to not to keep clear the potential area that can be invaded by the snow mass. So this is particularly important because the traffic and the vehicles should be stopped upward or downward in respect to the crossing of the gully, in order to keep the condition of safety for everyone. The last event that I want to show is a debris flow that is occurred the last years in June. In this case, we are talking about the Pont of Galli. So here you can see it's better to see that you are not able to see no more the road. The road is here. You can see maybe a vehicle that is keeping clear the road from all the debris and the rocks. And here you can see another picture from above the channel. And here, this is the road. So a huge amount of material, a huge amount of debris was channelized in this galleon was deposited on the road, and also in this case our system, early warning system, was able to turn on the traffic lights and thus stopping the traffic along the road, keeping condition of safety all around, during all the events. So to conclude, what are the critical aspects for the creation of an effective early warning system? This is, you can interpret as a take-home message. So it's really important a correct design of the early warning system, because if the design is not accurate, is very difficult and to create an effective early warning system. Another aspect that is important is redundancy, because in general all the early warning systems should be redundant. Then obviously you have to select the most performing radio components. For instance, in this case, the LoRa kit that we use, and that, as I said before, has allowed us to transmit all the signal correctly and continuously between the different node sensor. Another aspect that is important is the data interpretation. So this means, we can automate, we can, as I can say, the human contribution for the early warning system is still required, because we can keep some particular processes in an automatic way, but then we need to interpret all the data that are collected. And then the last point is the management, the maintenance of the early warning system, because without maintenance, we can install at first the early warning system, but then we can obviously maintain it in a good state, because early warning system should assure a continuous functioning during all the time, 24/7 and 7 days by 7. So thank you, and I just finished my presentation, so I left the words to Paola.
No, just to me that I want to say. Don't worry. Okay, just to say a few words to close the webinar. First of all, it's great to see a live application of the IoT, and especially if our radio module is included. I really loved it. I saw that there is no question for the moment. If you will have any question after the webinar in the next week, wherever, you can type an email to info@movax.it, and we will get back to you as soon as possible. So I would like to say thank you to Francesco, to Emanuele, to all the ones that participated in this webinar. And so I will say that this is the ending, and thank you so much to everyone. Bye. Thank you,
Ilenia.
Thank you,
Ilenia.
Emanuele.
Thank you,
Bye.
everyone. Have a nice day. Bye.
Thank you.
Bye.
Bye.
Bye.